Assalamu alaikum. I am Atia Fairuz Jahin, ID 20210208122. Today I will be reviewing one of the papers from PLOS1, and the research article is shown here: Experimental Evaluation of Stiffness Predictions of Multiaxial Flax Fiber Composites by Classical Laminate Theory. The objective of this presentation is to summarize the paper's key findings and, most importantly, to articulate its direct connection to the principles we have learned in this course on composite materials. In our course, we have established CLT as the fundamental methodology for predicting the macroscopic elastic behavior of a composite laminate, and it was based on the properties and orientations of its individual plies. This paper serves as a direct and practical validation of this very theory. It moves the concept from the textbook to the laboratory, testing CLT's accuracy on a specific emerging class of materials, and that is multiaxial natural fiber composites. The researchers fabricated multiaxial composites using two types of biaxial flax fabrics with a nominal orientation of plus minus 45 degrees, arranged in two different layups, A and B. Crucially, they identified that the actual fiber orientation in the fabric can deviate from its nominal value. To address this, they developed a novel called fast fiber orientation, or FFO method. It had used 2D fast Fourier transformation on scanned images to measure the actual yarn angles with high precision. In this paper, the data shows the actual orientation were not perfectly plus minus 45 degrees, and fabric was notably unbalanced. So, from the table, from this paper, we can see the experimental stiffness of this multiaxial composites was highly anisotropic as expected. So, the table 4 is a little bit lower on this paper. Let us find that. Here, it was presented for layup A and layup B. For the CLT predictions, the input parameters for the unidirectional ply were not fitted, but were determined independently. The longitudinal stiffness E1 was derived from the tests on uniaxial composites corrected for fiber volume fraction. The transverse stiffness E2 and shear modulus G12 were calculated using micromechanical models like the inverse rule of mixtures and the Halpern-Tsai equations, which are also core topics in our course. From figure 10, we can validate the critical finding, and this is the most significant finding. The CLT predictions, when using the actual FFO measured fiber orientations, showed excellent agreement with the experimental data here. But when the same CLT model used nominal plus minus 45 degree orientations, the error increased significantly to a mean of 0.5 gigapascal, and the earlier it was just 0.2 gigapascal, and these values were noted in that paper boldly. A sophisticated model is only as good as the real world data we feed into it. So from this paper, we can have takeaways like this paper successfully validates the classical laminate theory as a powerful and accurate tool to find multiaxial flax fiber composites stiffness, and also it actually follows two conditions. First, the uniaxial ply properties are properly characterized, and the second, actual fiber orientations in the fabric are measured and used, not just nominal values. This work directly connects our course by demonstrating the practical application and limitations of CLT. It underscores that for reliable engineering of composite structures, meticulous material characterization is not an optional extra. It is a fundamental requirement. Thank you. It was my presentation.